Welcome back to Basic Electronics. In this lecture, we will start with the binary or base 2 number system. We will see how addition of binary numbers can be implemented with logic gates. Finally, we will look at implementation of a logical function using only NAND or only NOR gates. So let us begin. We now want to discuss binary numbers, that is numbers in the base 2 system. But before we do that, let us look at our decimal system. And here is an example, 317. And let us ask this question, why is the value of this number 317? And the answer is, this 3 gets a weight of 10 raised to 2, this 1 gets a weight of 10 raised to 1, and this 7 gets a weight of 10 raised to 0. So that is 3 times 100 plus 1 times 10 plus 7 times 1, and that is how it becomes 317. And these numbers are called the digits, and in the base 10 system the digits of course can vary from 0 to 9, and the leftmost digit is called the most significant digit and the rightmost digit is called the least significant digit. Here is an example, 4153. Here the most significant digit is 4 and the least significant digit is 3. Now let us look at the binary system. Alright, so here is an example of the binary or base 2 system, and we notice that in each position we have only 1 or 0, and the weight that is assigned to each position is a power of 2. And this number, for example, is 1 times 2 raised to 4 plus 0 times 2 raised to 3 and so on. And if we calculate that, it turns out to be the number 23 in our decimal system. So in the decimal system we had digits, here we have bits. The digits could go from 0 to 9 and the bits can only have 2 values, 0 or 1. Here is an example of a binary number. The leftmost bit is called the most significant bit or the MSB. In this case it is 1. And the rightmost bit is called the least significant bit or LSB. In this case it is 0. Why is this called the most significant bit? Because it gets the largest weight. Similarly, the LSB gets the smallest weight. We will now discuss addition of binary numbers. But let's start with the decimal or base 10 system first, because we are already familiar with addition of numbers in this system. And then we will see the parallels between the base 10 system and base 2 system. So here is an example, 3179 plus 8015. How do we go about adding these two numbers? We start with the least significant digits, that is this column here. We add this 9 and 5. Now each one of these gets a weight of 10 raised to 0. So the sum here is 14. We take 1 as carry. Now this 1 has a special significance. Its weight is 10 raised to 1, which is 10 times higher than this weight. Next we add these two and we also add the carry and so on. In this case the carry is 0, so we only need to add 1 and 0, etc. And that is how we end up with this sum. Okay, let us now look at the binary or base 2 system. And before we look at addition of two numbers, let us look at these addition of bits here. If we are adding 0 and 1, what do we get? The result is 1. That means the sum bit is 1 and the carry bit is 0. If we are adding 1 and 1, then the result is decimal 2. Decimal 2 is the same as binary 1, 0. The right bit here is the sum bit, which is 0, and the left bit here is the carry bit, that is 1. What about 1 plus 1 plus 1? That is decimal 3, which is binary 1 1. So in this case the sum bit is 1, S, and the carry bit is also 1, that is C is equal to 1. So using these, let us now try to understand this addition example. So we want to add two numbers, 1011, which is decimal 11, and 1110, which is decimal 14. Where do we begin? We begin with the least significant bit. So we add 1 and 0. We get a sum bit 1 and no carry bit. Then we add this 1 and 1, and 1 and 1 gives us 1 0. So sum bit 0, carry bit 1, sum bit 0, carry bit 1. Again we add 1 and 1 here, sum bit 0, carry bit 1. Now we add 1, 1 and 1, so we get decimal 3, and that is sum bit 1 and carry bit 1. And now of course in this column there is no bit over there, so only the carry, so that is 1 here. And if we evaluate this number, that turns out to be decimal 25, as we would expect. Let us now generalize the binary addition that we saw in the last slide. Here is our example, and that will help us to see what should happen in the general case. Alright, so here is the problem. We have two numbers, first number and second number, binary numbers, and we want to add these two numbers. There are n plus 1 bits in each number, and we have A0 as the least significant bit in the first number and AN as the MSB. And the weights go from 2 raised to 0 to 2 raised to n. These are the carries. This C0 is coming from column number 0, C1 is coming from column number 1, and so on. And this is our final sum. S0 gets a weight of 2 raised to 0, S1 gets a weight of 2 raised to 1, and so on. Here is the block diagram for binary addition, and this first block performs this operation. That means it takes A0 and B0, adds the two, and gives us a sum bit S and a carry out bit CO here, and we have called that S0, so this is S0, and we have called the carry out as C0, so that is C0. Now this block is called half adder because it does not have a carry here, and all other blocks, all of these, are called full adders because they also include a carry. What about this full adder? Let us take this as an example. So we have two bits coming from the two numbers. We have a carry in coming from the previous stage, and as output this full adder must produce a sum bit and a carry out bit. So that is what we see over here. These are the two bits coming from the numbers. This is the carry in, this is the output sum bit, and this is the carry out. So in this case, for example, we have A1 and B1, A1, B1 there. C0 is coming as the carry in from the previous stage, and the sum bit is S1, S1, and the carry out is C1, C1 there, and so on. Alright, so let us summarize. The rightmost block corresponding to the LSB adds two bits A0 and B0 there. There is no input carry. This block is called a half adder, and each of the subsequent blocks adds 3 bits AI, BI, and CI-1 coming from the previous stage, and these blocks are called full adders. Let us now look at the implementation of a half adder with gates. So let us start with the truth table. So there are two tables in fact here, one for the sum bit and one for the carry out bit. When A and B are both 0, then the sum bit is 0, carry out is also 0. When A, B are 0, 1 or 1, 0, then the sum bit is 1, carry out is 0. And when A, B are both 1, then the sum bit is 0, carry out is 1. Alright, so these are the functions that we need to implement. So this S turns out to be A bar B plus AB bar. This term is A bar B and this term is AB bar. And that is essentially the XOR operation. And the carry out function is 1 only for this condition. So therefore that is A and B. So here is how the S and CO functions can be implemented. CO of course is just AND of A and B as shown here. And to get S we need to generate A bar and B bar, then A bar B and AB bar, and then finally put them through OR gate to get S. There is a better implementation and that requires a smaller number of gates. And you should take this as homework and verify that S is indeed A bar B plus AB bar in this case. Let us now look at how a full adder can be implemented. It has 3 inputs A, B and C in, the carry in coming from the previous stage, and it has 2 outputs, the sum bit and the carry out or CO bit. Okay, so let us construct the truth tables for S and CO. How do we do that? All we need to do is to look at the number of ones in each row. In this case there is no 1, so therefore the addition of these 3 will give us the binary number 0, 0. That is what we have here. In this case and this case and this case we have only 1, 1. So the addition of these 3, that is A and B and C in, will give us the binary number 0, 1, and that is what we see over here. In this row we have 2 ones. In this row also we have 2 ones, and in this row also we have 2 ones. And the addition of A, B and C in that case will be binary 1, 0, that is decimal 2. So that is what we see over here. In this last case we have A equal to 1, B equal to 1 and C in equal to 1, and when we add these we get decimal 3 or binary 1, 1, and that is what we see over here. So now we have the tables for S and CO, and let us now see how they can be implemented. So here is the K map for the sum bit, and unfortunately all of these ones are isolated, they cannot be combined with any neighbors, and therefore we have 4 minterms given by this expression here. What about CO? That is the K map for the carry out bit. In this case there is some minimization possible. We have 4 ones and we can cover these 4 ones with 3 rectangles, and therefore we have 3 terms, each term having 2 variables. Let us now look at implementation of logical functions with only NAND gates. It turns out that the NOT, AND, OR operations can be realized by using only NAND gates. And let us look at these one by one, starting with the NOT operation. So here is the implementation. We have a NAND gate here. We connect the 2 inputs together and connect our input variable A over there. So what do we have at the output? We have A dot A bar, and since A dot A is nothing but A, we get A bar at the output. Here is the implementation of the AND operation, and let us see how it works. We have one NAND gate here, so at this point we have AB bar, and then we have connected this inverter. So therefore we get at the output AB bar of that, and that is nothing but AB. So that is the AND operation. and here is the OR operation. This is an inverter, the same as this one. So we have A bar here, B bar here, and then we have A bar and B bar and the not of that, like that. And that, by De Morgan's theorem, is nothing but A plus B. So that is our OR implementation. Let us take up this exercise. Implement y equal to AB plus BC D bar plus A bar D using only NAND gates. And as we have seen in the last slide, this is how we can implement the NOT and OR operations with NAND gates. So for this function, what is our step number 1? Step number 1 is to implement this OR operation. And let us assume that we have gates available to us, NAND gates available to us with 2 or 3 inputs. So this is similar to this A plus B operation here, except we now have A plus B plus C because we have 3 terms, and that would be A bar dot B bar dot C bar and the bar of the whole thing. Alright, so let us write this in this format, like that. So this AB can be treated as A, and since we have A bar here, we have AB bar, and the same thing applies to these terms as well. So that is our first step, and that is the implementation of the first step. So we have AB bar here, BC D bar of that, and A bar D bar of that, and all of those are applied to this 3 input NAND gate. That should give us our output Y. And now we need to figure out how to generate each of these. How do we obtain AB bar? That is in fact nothing but the NAND operation itself, and therefore all we need to do is to connect a 2 input NAND gate here with inputs A and B, like that. What about this term? We have BCD bar and the bar of that. So this can be achieved using a 3 input NAND gate with inputs B, C and D bar, and D bar can be obtained by using this equation. So we use a NAND gate with inputs D and D. So that is B, C and D bar has been obtained with this NAND gate by connecting these 2 inputs together and then connecting that to D. And this term can also be implemented using a NAND gate, a 2 input NAND gate with inputs A bar and D, like that. So this is A bar and this is D, and again A bar has been obtained from A using this NAND gate. So this is our overall implementation of the logical function Y using only NAND gates. Let us now look at another approach of implementing functions with only NAND gates, and we will take the same example that we saw in the last slide, namely Y is equal to AB plus BCD bar plus A bar D. What we do first in this approach is we implement the function with AND gates and OR gates as shown over here. So this term here is AB, this is BCD bar, and that is A bar D. These are the AND gates which we have used, and these 3 outputs are now ORed together to give us our final function. So that is our starting point, and subsequently we look at the function that each of these gates is performing and implement those functions with only NAND gates. Let us start with this gate here. It's an OR operation. How do we implement OR operation with only NAND gates? We can use this identity here. So what we need to do is to generate A bar and B bar first, and then perform a NAND operation on those. If we call these 3 variables as P, Q and R, then what we need to do is to create P bar, Q bar, R bar, and then perform the NAND operation on those three, and that is shown over here. So if this was P, this is P bar. If this was Q, this is Q bar, and so on. And now we have a NAND operation on P bar, Q bar, R bar, and that gives us P plus Q plus R. In a similar manner, we can also replace these gates with NAND gates. For example, if we have this AND gate, it can be replaced with an AND gate followed by an inverter. And we can do the same with these two gates as well. So these three gates can be now replaced with an AND gate followed by an inverter, as shown over here. Now we notice that there are these two inverters connected in series, and they are essentially redundant and they can be removed. If this was X, then this would be X bar, and we get X here once again. So these two can be simply eliminated, that is replaced with a wire. And the same thing can be said about these two inverters and these two inverters as well. So now the inverters have been eliminated and our circuit has been simplified. And finally, we can replace these two inverters with NAND gates, and we have already seen how to do that. We take a NAND gate, tie the inputs together, and that serves as an inverter. Alright, so that is our complete implementation of this function y using only NAND gates. Next example, implement y equal to a plus b plus c using only two input NAND gates. So now we have this restriction. We can use NAND gates with two inputs only. Alright, and here are our equations once again for implementation of the NOT, AND and OR operations using NAND gates. Here is our step number 1, and what we have done here is we have grouped this a plus b together. So we are treating a plus b as one entity now, and let us call that x, for example. So we have now y equal to x plus c. And how do we implement x plus c using NAND gates? We can refer to this equation here. So x plus c would be x bar dot c bar and bar of that. So that is how we can implement this first step. So c bar and then a plus b bar and the NAND of that. Now let us see how to generate each one of these. C bar is easy to generate. We just need to use this equation. So we use a NAND gate, connect the two inputs together and connect that to C to get C bar. What about this operation? This is the NOR operation and it is not there in this list. So what we will do is we will generate a plus b bar from a plus b using the NOT operation, like that. So we have a NAND gate with inputs tied together. We apply a plus b here and then we get a plus b bar over here at the output. And now we know how to generate a plus b using this last equation, and that completes our implementation. It turns out that we can also use NOR gates to implement logical functions without using any other gates. So the NOT and OR operations can be realized using only NOR gates. And let us look at these one by one. Here is the implementation of the NOT operation using a NOR gate. So we have a NOR gate here. Its inputs are connected together and that is connected to the input A. So at the output we have A plus A bar, like that, and a plus a is nothing but a, so therefore we have a bar. So that is the implementation of the NOT operation. To implement the AND operation, we can use De Morgan's theorem, that is a and b is a bar plus b bar and the bar of the whole thing. Alright, so what do we need to do? We need to generate a bar and b bar using NOR gates, and we already know how to do that. This is the inverter that we can use. So from A we generate a bar, from B we generate b bar, and then that goes to this third NOR gate, and then we get AB at the output. What about the OR operation? A or B is nothing but A or B bar and bar again. So this is the first NOR gate that gives us A plus B bar, and the bar of that again can be obtained using this inverter to get A plus B at the output. So at this point we have looked at implementation of logical functions with only NAND gates and also with only NOR gates. Now the question that comes up is, are we doing this for fun, or is there some practical implication of all of this? The answer is that these are actually practically very relevant, and let us see why. Implementation of functions with only NOR or only NAND gates is more than a theoretical curiosity. There are chips which provide a sea of gates, that is a large number of gates of only one type, say NOR gates or NAND gates. And these gates can be configured by the user through programming to implement functions. And that is where this implementation with only NOR or only NAND is very useful. Let us implement this function y equal to ab plus bc d bar plus a bar d using only NOR gates. And these are the equations we have looked at for implementation of NOT, OR, AND operations with only NOR gates. So what is our first step? We have the OR operation here, and here is how we can implement the OR operation. We have to do a plus b bar and then NOT of that, like that, and that can be implemented like this here. So this NOT operation, the bar on top, is provided by this NOR gate, and AB plus BCD bar plus A bar D bar is given by this first NOR gate. So what are the inputs to this first NOR gate? AB, BCD bar and A bar D, like that. And now we need to see how to generate each of these. How can we get AB? Here is the equation. First we can generate A bar from A using this equation, and also B bar from B, and then we can use an OR gate to get AB, like that. So this NOR gate gives us A bar, this NOR gate gives us B bar, and then finally this NOR gate gives us AB. Now these terms can also be similarly implemented, like that, and you can check that out. So that completes our implementation of the logical function y using only NOR gates. To summarize, we have seen the meaning of the terms half adder and full adder, and how they can be used to add two binary numbers. We have also seen how a logical function can be implemented using only NAND gates or only NOR gates. In the next class, we will start looking at more complex elements such as multiplexer. So see you next time.